Ah, es verdad. Oops. Ignore this. Ignore this part. Okay. So let me trace. Many of you have already heard this topic. I'm going to try to go beyond the line of, hey, that's interesting, but I didn't fully understand. Hopefully, some of you will understand fully this time. So the idea, this paper is named Random Access Codes via Quantum Contextual Redundancy. And the main idea is to encode classical information, bits, into a quantum system, and then retrieve part of this information by measuring the system on a certain basis. So depending on which basis we choose, we're going to retrieve one part of the information or another. So I've chosen to depict it with colors. Let's say the red-colored observable helps us retrieve this part of the information, just as an example. And you do it with some fidelity f. So this doesn't necessarily aim for 100%. It just uses a certain number of resources and reaches some fidelity. So this is the main idea. This is what a quantum random access code is. This comes from the idea of a random access code, which is essentially this basic idea, but the quantum adds the use of quantum resources to gain some advantage. So there are some previous examples of quantum random access codes in which they store 3 bits into a single qubit and then retrieve any of these bits with some fidelity. So for example, you have a block sphere and you take one of the corners of this square, you're going to get some statistic for x, y, and z observables. X meaning that you can get either plus or minus on your outcome, y meaning that you can get R or L on your outcome, and Z meaning that you can get 0 or 1 on your outcome. So for example, when you measure this state, you're going to get a higher statistic for plus, for L, and for 0, respectively, when you measure X, Y, and Z. So if you send a single copy of this state and this to user, let's say Bob, and you want Bob to retrieve one of your bits, what Bob would do is he chooses which basis to measure because he chooses which bit he wants to retrieve. Then he measures in the corresponding basis. For example, this state, he measures on basis X. And he has a higher probability of obtaining plus than what he has of obtaining minus. And this probability is 0.789. So essentially, by sending a single qubit, you have given Bob the chance to retrieve 1 out of 3 bits with a sort of high probability. In any case, higher than what any classical strategy could achieve by sending a single bit. So in average, classically, if you made a strategy to send the most common bit that he is encoding, he would just send you something, and you would get an average fidelity of 0.75. So essentially, you can get some quantum advantage, even in this small scenario. There have also been, yeah.
When you say you are measuring what the new value, or I think
all situations, all possible configurations. So for example, if Bob has, there are 8 possible configurations of bits, because there are 3 bits. If Alice does the strategy of sending the most common bit from her set, then in average, Bob will predict with 75% accuracy which bit was the correct one. So in some scenarios, for example, if Alice has bit 111 and she does the strategy of sending the most common bit, in that specific scenario, Bob has a 100% chance of retrieving that.
what I mean is, because you said 1 bit, but what you want to say is that you send several copies of the state, right?
If you send several, you increase the strategy. You increase the fidelity. Single, yes. So this for the classical, you send a single bit, and Bob has to retrieve 1 out of 3 bits, but he just has this single copy. So this could be easily improved by increasing the number of samples sent. Okay, so the thing is, even at this point, there is a little bit of quantum advantage. This has been extended to systems of larger size because, as you can see, this is just a single qubit. So when doing this in larger size, let's say for a 2-level system, like this scenario, we are working with 3 possible observables, x, y, and z, which are called mutually unbiased spaces because their eigenstates, let's say, because their outcomes are completely incompatible. If you measure in x, then you cannot measure in y. So, in general, for any D-level system, you can get at most D+1 MUBs, D+1 mutually unbiased bases. So this is the general approach of how to extend to systems of larger size. So the idea is if you send one qubit, meaning one system of D levels, you can choose one DIT, meaning one DIT to retrieve from at most D+1 options. So Bob chooses from D+1 bases, he measures the system on that base, and he has some probability to retrieve the correct state from that base. So that's the general idea for what n-level Quracs are. But they have the problem that they don't really increase fidelity that much. They have a small scale quantum advantage. In fact, there's less than 10% fidelity increase. And according to the current studies, they peak at D equals 5. According to them, because there are some mistakes on the latest papers that appeared of this. But the thing is, they claim that the peak of this approach is at 5 levels, which is less than 3 qubits. And another big deal is that this approach has a fast decaying fidelity. The fidelity decreases very fast as the number of levels increase. So to increase the retrieval, you would need a lot of samples, and this number of samples do not compensate for this fall in fidelity when increasing the number of D levels. Note something, that the number of D levels increases exponentially with the number of qubits. Yeah, so this decreases very fast. Okay, so these are the 2 challenges that we try to solve in our approach. What has been done so far is to use MUBs as the basis in which you measure some quantum systems. We propose something slightly different. So far, MUBs have been used. They have the advantage that, let's say, the relationship between MUBs is pretty clear, that their outcomes they do not commute with each other, and that the outcomes of one mess up with the outcomes of another. You cannot measure in one MUB and then in another. The properties are pretty straightforward. What is not so straightforward is the set of them. In fact, to compute the set of NUBs for n qubits in general is non-trivial. It's a non-trivial problem. So we propose something different, a scenario in which the relationship between your observables is not so straightforward, but the observables themselves are pretty straightforward. So we use something that we call parity observables. For 1 qubit, they remain the same, x, y, and z. But for 2 qubits, instead of using this, which in the case of MUBs was measure the first qubit in basis x, measure the second qubit in basis y, that's the first PO. And the second PO was measuring y and y. This one was measuring z and z. This was measured in such a way that you get outcomes of the Bell basis rotated into this basis. Well, these were the MUBs used. Instead, we use these observables, which are observables with only 2 outcomes. So, for example, observable XX, in which you get +1 in one scenario and -1 in another scenario. You split the eigenbasis in half in any of these cases. You can define this basis in such a way that you have exactly 3 to the n parity observables. I will talk a little bit more about the properties of these observables in the next slide. But for now, let's just say that the set of them is very well defined. What is not so well defined is the fact that some of them commute and some of them do not. So that must be computed later on. And the advantage, we will be looking at the advantage of using these observables. Overall, when using this approach, we are able to propose a protocol in which you obtain some better scalability than what has been done so far on quantum random access codes. And our fidelity is non-decaying. In fact, we can achieve a constant fidelity for any number of qubits. And this allows us to achieve some quantum compression advantage from 18 qubits onwards. And we could project onto how many qubits we would need to store a very large amount of data, let's say the totality of Google Drive servers, we would need a certain number of systems of 44 qubits. Many of them, by the way, but we would do this with some quantum advantage. Okay, so let's get onto how we get to this point from this approach. So some forward, let's distinguish between these two kinds of measurements, a regular measurement and a parity observables. So for example, if you have a circuit and you measure each one of the lines of the circuit on basis Z, then we are doing the equivalent of measuring, well, these three observables, each one for each line, and having a total number of outcomes of 2 to the n. So in this case, we can distinguish between all possible elements of the basis, of the Z basis. You get a different outcome for each one of them. So this is the observable spectrum of this scenario. Parity observable, however, only has two different outcomes. It would be like performing this on this circuit. So for example, a control node from the first to the second one, a control node from the second one to the third, in such a way that when you measure this last one, if you have an even number of ones, you get a +1 as eigenvalue. And if you have an odd number of ones in total in your qubits, you get a -1 as eigenvalue. So you only get in this observable, which is tensor product of Z, 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 either λ0, first eigenvalue, or λ1, second eigenvalue. And you're splitting your set eigenbases in two pieces, the even pieces, sorry, and the odd pieces. And this can be done not only for Z, 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 but for any combination of Paulis tensored together. So we have 3 to the n possible combinations of these kind of observables, and we will exploit them all. These are the parity observables. They also have an interesting property. It's the fact that since they only have two outcomes, they aren't fully collapsing your state. So some set of the parity observables commute with each other. For example, for 2 qubits, XX commutes with YY, which also commutes with ZZ. So if you measured a certain state in XX, you could then measure it in YY and then measure it in ZZ and not affect the statistics in theory. So what we have here is what we call a context of measurements. We could measure this whole context for a given single copy of your state. As a context, contexts have the property of having a common set of eigenstates. There's a set of states which is eigenstate to each element of the context. We will be specifically exploiting these eigenstates as they yield, let's say, extreme statistics for all parity observables of the context. An example of context eigenstate for that specific context is the Bell state. So for example, Bell state yields is an eigenstate which yields eigenvalue +1 on XX, -1 on YY, and +1 on ZZ. And has completely homogeneous probability distributions for all the other observables of the parity observables here. So another property that it's interesting to note is that we can reorder, at least in 2 qubits, we can reorder the parity observables in such a way that every context forms either a row or a column. And those that form a row, any context eigenstate of the context has a product of eigenvalues which yields -1, and the columns multiply to +1. So that's an interesting property which is related to contextuality. This is a useful representation for 2 qubits. It will just help us to understand, but the extrapolation of this to larger systems is not easy to visualize. What we need to know, though, is that the number of POs, the number of parity observables, increases exponentially like this, 3 to the n, because 3 Pauli observables to the n. And the context size, meaning how many POs form each context, increases like this, 2 to the n -1 +1. I won't get into details how we get this. And the size of the basis of a context eigenstate is of size 2 to the n, like any basis, a full basis. Okay, so how do we use this to store information? Essentially, the easiest way is to map 1 bit from each one of the parity observables. So for example, to map one bit from observable XX, another one from this one, and so on. Here we would have 9 bits. The quickest way to do it is to say, okay, we will define the concept of preferred parity. So whichever parity, either +1 or -1, has higher probability is the encoded bit. Yes?
What do you mean with this parity thing? Like the case before with the memory square? You said that some context has some parity and others some other parity. What do you mean exactly?
Yeah, each PO has 2 eigenvalues, +1 or -1. That's why we call them parity. And what I meant by a parity product is the product of the parities when measuring on XX, YY on ZZ. So if you take any state and measure on XX, you get an outcome, either +1 or -1. Then you do that. On that very same state, you measure on YY, and then you measure again on ZZ. The product of those parities will be -1. There's no way it is not. If it's +1, there's a problem with your measurement. So the 2-qubit systems satisfy that property. So you cannot get statistics in which the product is +1. So parity is going to be either +1 or -1 when measuring any of the POs. So if we use the concept of preferred parity, we can map 1 bit from each one of the POs, each one of the parity observables. Okay, so for example, let's say we have this collection of information, this collection of parities, which we map to each one of the parity observables. If we have this collection, specifically, let's say -1 for XX, +1 for YY, and we want to store it efficiently, we could use a collection of context eigenstates, for example, a context eigenstate which is kind of like a Bell state, which yields statistics of -1, +1, -1, respectively for XX, YY, and ZZ, and the same for these 3, and the same with this state for these 3. So we could use 3 context eigenstates to fully encode 9 bits, in principle. What I haven't told you yet is that this configuration is a lucky one, because you're not always able to have a context eigenstate which fully matches in a given context. So the ones that I have circled in red and blue are the ones that, given this PPC, have an eigenstate which fully matches the context. So we'll get into that in a moment, but for now, in principle, we could be using a set of n qubit states to encode 3 to the n bits. So that's the main idea. Encode 3 to the n bits using a certain collection of n qubit states. Okay, so that's the main idea so far. The summary is we're storing information in quantum systems, which is we're storing this information into these quantum systems, and then we measure one of these states, one of the encoded states, in our PO context and retrieve a part of the information encoded. So for example, if you measured in this context, you would be retrieving this information over here, these 3 bits. Okay, that's what we have so far. This is our QRAC, the basic skeleton of our QRAC. However, what I mentioned, we were working with a lucky context. This context in 2-qubit systems corresponds to those that have the largest number of let's say, representable eigenstates. What do I mean with this? Let's say you have a random context, a random collection, a random preferred parity configuration, let's say a random collection of +1s and -1s. This one is a lucky one because in these 3 rows, you have a context eigenstate which fully matches these values. And in this column, you have context eigenstates which fully match, meaning these 3 rows are satisfying the Mermin-Perez condition, and these 2 columns are satisfying the Mermin-Perez condition. Out of logical necessity, it is impossible for this column to satisfy it. So you will never get 6 contexts that match. So at most in 2-qubit systems, you can get 1 which matches, 3 which match but are not aligned, 3 which match, and form 3 rows in a row, and 5 with match. Which color? Let's say which have 3 rows in a row necessarily. So in these two scenarios, we are able to encode the full 9 elements using only 3 context eigenstates. In these two scenarios, we cannot. So these are the lucky cases. In fact, these are the minority. And we should then do something to take advantage of these and try to encode our information always in the lucky cases. So to do this, we do a little trick in which instead of storing 3 to the n bits in 3 to the n parity observables, we encode only half. So we will only be encoding 3 to the n minus 1 over 2 bits, because that's a half rounded down. Then this would allow us to always choose the lucky PPCs and always have an advantage in encoding the information. So we will have some wiggle room, some additional degree of freedom, which we exploit to our advantage here. So when we do this, our encoding changes a little bit. Instead of working with 9 logical bits, we're working with 4 logical bits, talking about 2-qubit systems. So for example, this could be our initial logical bit string. We would map each logical bit string to a pair of parity observables. And we would say, okay, each one of the bits we are using tells us a correlation between these two observables. So this bit 1 means that the preferred parities of these two observables have to be different. 1 means different, 0 means the same, and 1 means different. So we would be encoding 4 bits using 8 POs, and we'll leave 1 out. And then when we do this, we can choose, since we are only stating that they have to be different, they can be -1 + 1, or contrary-wise, +1 - 1. And if they have to be the same, they can be +1 + 1, or -1 - 1. So we can choose a convenient preferred parity configuration, which maximizes how many of these rows and columns are colored, for example, for 2 qubits. So we need to do some classical training to choose which PPC to use, a highly redundant one at that. And this could end up with us choosing, for example, this one, in which, once again, we can encode all of this information using only 3 context eigenstates, which tell us these statistics, and these statistics. So we would be using a certain number of states, which is reduced thanks to the fact that this structure is very redundant in terms of compatibility with context eigenstates. Okay, and lastly, the retrieval is essentially taking our set of states in which we did the encoding and measure them on a certain basis. So for example, you measure each one of the states on a given basis, OK, for example, which is this value, and those that switch their outcome at some point on repeated measurements are those that do not belong to the context. What do I mean by this? For example, state psi2 is this state over here, which corresponds to this context over here, which has these 3 elements. And when measuring on set x, then, well, set x is here, so you get a constant output of +1. But the other ones eventually switch because they have statistic of 50-50. So by doing these repeated measurements, you can discard those that do not belong to the context and finally obtain the correct encoded parity, which is +1 in this case, this value over here. And as you can note, when we do this filtering process, at every stage of measurements, those that are not defined on the correct context have a 50% chance of being discarded after the first measurement. So the number of steps is going to be a logarithm of 2 of the size of the selection. And well, this is something fully necessary to do the statistics of how efficient this method is. By taking all of these values, by doing an analysis of how many logical bits, how many compatible preferred parity configurations there exist, how many states are needed, and how many steps are needed for retrieval, we can do a full statistics of the protocol. Yes?
Sorry, maybe I'm missing something. Why do you need the set parity observable?
The set?
Yeah. Do you know about that you include in the table?
Because, well, they are an odd number of parity observables, and I need to encode in them in a 2-to-1 fashion. And so I need to just throw one out, because I cannot pair it with something. So the idea is that I want to do a 2-to-1 encoding, let's say 1 bit using 2 observables, because that allows me a little wiggle room in choosing these values, which allows me to pick one of the cases which are more redundant, which is more convenient for the sampling. So if I'm able to do the 2-to-1 encoding, I get some sampling advantage. But since this number of POs is 3 to the n, that's always odd. And if I do a 2-to-1, then I need to throw one out. So I choose to just throw this one out. It could have been any other one.
Is it useful in any way?
I mean, there are 3 to the n. Throwing one out doesn't hurt the protocol much. Yeah, it's not a big deal. Yeah, that. Any other questions so far? No? Yes?
If I'm not mistaken, what is happening here is that the only state which is an item state of the observable set X is
Psi2.
Yeah. Then, and you are using 3 states.
Mm-hmm.
So you are using 3 contexts, right? But you have 5 of them. So why is it better to have 5 than 3? If you are using
It's not better. It's the same.
Okay, it's the same.
Yeah. But yes, when we work with a larger number of qubits, it's not going to be so simple as to say, okay, these 3 fill up the space. It's much more complicated shape, so you will always try to maximize the number of redundant contexts, whatever the case. So for 2 qubits, 5 with 3 in a row is the same as 3 with 3 in a row, but no for larger systems.
How do you choose the test basis because you have the option is the 1, the 3 in a row, and the 5, no?
Mm-hmm.
How do you know what is the test basis?
So basically, I try to maximize the number of redundant contexts, by which I mean the number of situations in which a context eigenstate can fully match the PPC.
And if you make a very big basis, it's very complex.
It's complex. Yes, there's a sub-training for that. So there's an optimization process to maximize the number of redundant contexts. And then there's another optimization process to choose which actual context eigenstates to use. So it's a 2-stage optimization. Yes, so if different choices of which collections of PPCs to use will yield different ways to encode the information. And it's such a big space that it's impossible to guarantee that you're using the optimal one. It's just, so the best idea is just to try to get a good one, because it's a very big space. Yeah, so it's a 2-stage optimization. You optimize which PPC to use, and then you optimize which context eigenstates to use within this PPC to try to encode it as efficiently as possible. Okay, so I'm skipping a mathematically hard part. Using all of this information, we built some statistical models to find out how many context eigenstates are needed, how many are needed to be selected, how many retrieval steps are required, which I already told you is the order of log 2 of this, as you can see. And we find out that the fidelity that is obtained in the end can be constant. And given a certain number of repetitions of the protocol, let's say this number, you can achieve this constant value of fidelity. This number of repetitions is high, but it's a constant overhead. It doesn't change with the number of qubits. So given a certain number of repetitions of the protocol, we can achieve a very high fidelity, which is constant. And in general, let's say the total number of 2-level resources used is a product of the context eigenstate selection size, how many, the context eigenstate selection size, how many samples are needed because of the number of retrieval steps, how many qubits per sample, because that's the size of the qubits the system's used, and how many repetitions. We multiply all of this together, and it yields us this order of magnitude. And when comparing this to the classical analog, this is the number of resources, of two-level resources used, and this is the number of two-level resources which you would normally need to encode and retrieve of the order of 3 to the n bits. Let's say 3 to the n. And for more than 18 qubits, we have some quantum advantage. This number is lower than this number. So there is some, this can be considered a compression protocol for n equals 18 and onwards. And if we extrapolate to a total number of encoded information equal to what Google Drive right now holds, we will be working with 44 qubits and this number of systems, which, if we want to know a comparison, would be like comparing storing 800 gigabytes in 1 billion users in 26.4 kiloqubits per user. So you can see it's like jumping from 800 gigabytes to 26.4 kiloqubits. Yes?
If I understand well, you wouldn't need any training process in the classical storage.
Yes, that's a straightforward thing.
How would the optimization process that you are taking, because you have to solve a combinatorial problem to choose the PPCs that give you the maximum expressibility. So how would it affect the quantum advantage and that complexity order?
Versus classical compression protocols, let's say.
Yeah, because there you are only including the encoding complexity, but not the training one. And you have spoken about activation process.
Yeah, there's an interesting thing here. Classically, I'm thinking as if I were working with data which has reached maximum classical compression ratio. So it cannot be classically compressed more. Even in that scenario, in which you have information that has reached its minimal entropy, even in that scenario, you can get some compression ratio from contextual compression, which classically you can no longer do. So,
to achieve that order of advantage, you need to go first through the optimization, and that adds some complexity.
yeah, but it's not. Let's say you still have some compression ratio. There's a cost to your compression, but there's no comparison. There's no classical comparison.
He's talking about the variation of
Because the complexity of the problem that you have to solve of picking 1i minus 1 and check all the possibilities scales 2 to the n. So in my mind, that combinatorial process of checking which would be the best PPC will be something that will have a cost of 2 to the n. So if you include the training cost to that compression, the cost would be similar to the classical one.
But when doing the encoding, we cannot include the cost of computation to find how to encode in the units of the encoding. It's two separate things. So one is the computation cost to reach the encoding, and the other one is the number of resources you have once you reach the encoding. So this is the number of resources once you reach the encoding.
But in the case of the classical, you do not need to do that.
Yes, it's a straightforward thing, no cost.
All complexities are quite similar.
Why? Because the calculation is the same in different fields. So you only have to do it once. Information that you have to do.
Yeah, you don't have to use the calculus optimization program for each problem. For each, every time you have the data, each time you have a different data, you have to make optimization or
Yes, you do.
the system.
Yes, you do.
So you have to make six for all the systems, to 6, 10 to 11.
No, not for each system. So, yeah, you do. So for a given set of information, you train once, and you find which context eigenstates to encode in. Then you encode them, and that's it.
Yeah, okay.
And once you do that, you have some compression advantage in the number of encoded units that you need to express all of that data. So the advantage, the bottleneck is in how many units you use to encode. But yes, there has to be a cost in how to compute which to use. Yes.
Here, so you put this nice example with the Google Drive thing, and you say you are using systems of 44 qubits. You have any like intuition of how hard is it to find the redundant contexts of 44 qubits?
Yes, very hard. I haven't fully solved the problem. That's the hardest part to scale. Yeah, that's the reason why we cannot solve chess with this yet, because if we extrapolated this, we would only need 100 qubit systems to do it. The hard part is actually finding the correct PPC and finding the correct context eigenstates. That's the hard part of the protocol, that computation. So this has applications to decision trees, because if you have noted, we encode information into quantum systems as long as we only retrieve part of the information. So we can encode a large amount of information, but you only retrieve one part at a time, which is readily applicable for decision trees because you have a large size for the tree, which increases exponentially in the number of branches, but you only need to take one decision at a time. So you could encode a brute force strategy for something and consult it as you see fit. Let's say, what do I do in this scenario? You take this route. And in this other scenario, this other route, and so on. But the size of the tree is huge. But this tells you a roadmap of what to follow. So this is readily applicable to brute force strategies in general. So for example, if we used it for chess, which has this number of board configurations, and a branching factor of 35, meaning 35 options per turn, you have in total this number of strategies, 35 to the power of 2 to the power of 155, which is very big. You could encode all of that using many 100 qubit systems in this approach and consult one branch at a time efficiently. The hard part, of course, is actually computing which systems to use. Yeah.
I have a very nice question that is coming to my mind in this moment that is quite disconnected. But do you have a full solution for the context for n qubits?
Sorry, the what?
For n qubits.
Mm-hmm.
Does it help to solve it for n+1?
You have the solution for n qubits. Can it be used for the n+1 case? I have no idea. n+1. Yeah, I cannot answer that quickly. Yeah, it's an interesting idea to work this constructively. No, inductively, where was it? Yeah, it's an interesting idea.
Because it looks like possible because you want to have all the parity context you want to keep that you can use it for. Of course, it will be exponential, but the exponential max.
And there's also, I have thought of the context eigenstates, which are basically GHZ states extended to a big size, but we could also work in sub-partitions in which you compute one part and another part and just have them be separable states. That's an approximation which could, let's say, tackle the problem a little bit. And yeah, this is a summary of what I have shown. We have proposed a correct protocol which solves the problem of fidelity of previous correct protocols. It achieves a certain compression rate above 18 qubits. It can compress a large amount of information and is readily applicable for cases in which you want to store a large amount of data but only want to consult pieces of it at a time. If you want to consult all of them, do not use this. This is basically for the cases where you have a large amount of data and only want to consult pieces at a time. That's where advantage lies. Yeah, that's it. Yes, Carlos.
I have a question. If I am not mistaken, when you, for example, in the case of chess, you want to check one of the positions or whatever, you have to destroy many systems, right?
Yes.
Okay.
So you need more than a single sample.
To be able to initialize again efficient way, right?
So there are two ways to think about this. You could be talking about a circuit which actively produces the state of your set, But of course, the variables you need to produce such system is greater than the number of degrees of freedom of the output itself. So it's a lost purpose. And you could also use a bank of pre-prepared quantum state, which is not up to current hardware capacities. So that's an open question.
I have another question. Have you, so do you see a relation of this thing with error correction?
Yes, there's an interesting comparison between the fact that the toric code uses, let's say, this, the stabilizer code use this to protect the data, where I use the redundancy to express it in less units. So two ways to the same basic element, redundancy. Redundancy for either protection or compression. I don't have a full comparison of this versus the surface code, but I think that's the main principle. Yes. Okay.
Congratulations. The improvement with respect to previous versions is substantial.
I'm glad I took out the graph that I liked a lot, but it was too mathematically complex. Okay.
In fact, I think this was the first time that you get a question.
Yes. Yes, that's the thing.